Hey, so this video is going to be talking about calorimetry, specific heat, and how to actually calculate delta H values. So before we dive any further into more of those specific topics, I just want to talk about some other units of energy that are commonly used. So up until this point, all we've really talked about is kilojoules. As you might be able to infer by the name kilojoules, that means also energy can be measured in joules. Another one that you've probably heard of is calories. So calories is what we usually see on our food, and that communicates how much energy is in the food. So that is another common unit of energy that's used. Fun fact, which is kind of obnoxious. You know how we say like our food has like 200 calories? That's actually a lie. Our food is actually all measured in kilocalories. For whatever reason in our culture, we've dropped the kilo and we just say calories. So when your food actually has 200 calories, it's actually 200 kilocalories. Fun fact. So to keep in mind how we're going to convert between all these different units of energy. So in different circumstances, one unit may be more appropriate than another. So you need to feel comfortable converting between them. So for example, there's 1,000 joules in a kilojoule, just like there's 1,000 meters in a kilometer. There's 1,000 calories in a kilocalorie, same thing. The unique one here is this. 1 calorie is equal to 4.18 joules. That is going to be our main conversion factor between calories and joules. Because like I mentioned, in some instances, calories is more appropriate than joules and vice versa. So this is just something that you need to feel comfortable with. And again, your main bridge is 1 calorie is equal to 4.18 joules. And then the other two is just 1,000 per 1 kilo, depending on which one you're talking about. This is just fun, purely just for fun. But just to kind of bring this idea back. So I've got a can of Coke from the United States here. And if you look, obviously it says how many calories are in there, 140. And if you look at the can of Coke from the United Kingdom, it actually lists kilojoules and kilocalories together instead, which I think is kind of interesting. So not only does it list both common forms of energy, it actually says kcal, where ours just says calories. If you're noticing some difference in values here, this is kind of annoying about the UK Coke. Nutrition information, typical values per 100 mils. And if you see, 1 can is 330 mils. So you've got to take all these values and multiply them by 3.3, which is a little silly. If you're following along with me on the notes, this stuff is kind of just for fun. So honestly, if you want to look through it, that is totally fine. But it's not something that you're going to actually be tested on. Here is where the meat of this is. A calorimetry test. So as you're looking at this word here, you might recognize calorie, and then metry means measure. So calorie measurement and energy measurement test. So this is a way to measure how much energy is present in whatever substance or reaction or anything that you're looking at. Our equation is this. Q is equal to MC delta T. So Q is equal to M times C times delta T. Some of these values are new. Some of these are familiar. The first one you need to look at here is Q, is a measurement of energy, and this is really important. It's a measurement of energy in joules. Okay, remember how a lot of our delta H values were in kilojoules, so that's just something to be mindful of. I'll explain why more in a minute here, but this equation, the energy is always going to spit out in joules. The M stands for mass in grams. Specific heat, which is a new term that I will describe in more detail shortly. The unit for this is always joules per gram times degrees Celsius. So notice that since the specific heat is measured in joules, that's why the energy will also be in joules. And then delta T is change in temperature. Remember, delta always stands for change. So this is the change in temperature of whatever you're looking at. And this is always measured in degrees Celsius. So specific heat, this is our new term. This stands for the letter C in the equation Q is equal to MC delta T. Your definition of specific heat is the amount of energy required to heat 1 gram of a substance 1 degree Celsius. So if you kind of dig into that a little bit more, specific heat is probably a concept you've been very aware of, even if you didn't actually know its definition. So for example, my favorite example is like, so it's summer, it's nice out. You go to the beach, you leave your car in the parking lot, you come back an hour later, and let's say you've got like cloth interior. You slide in like in your swimsuit into the cloth interior seat, you feel totally comfortable, and then you grab the seatbelt buckle and you accidentally touch your arm as you're bringing it across, and it burns you, okay? So the cloth seat, totally fine, totally not warm. The metal buckle burns you. They were both exposed to the same energy, right? They were both exposed to the same amount of sunlight. Why is one so much hotter than the other? Specific heat. The amount of energy required to heat 1 gram of a substance 1 degree Celsius. Metals tend to have really low specific heats, which means it doesn't take a lot of energy to heat 1 gram of a metal 1 degree Celsius. That's why metals get so hot so quick. But something like cloth or fabric has really high specific heat, meaning it takes a lot of energy to heat 1 gram of that substance 1 degree Celsius. So I've got two values here, water and iron. So even imagine like boiling a pot of water, right? The pot itself gets really hot. The water takes a really long time to boil. That's because of those different values of specific heat. So for example, it takes 4.18 joules of energy to heat 1 gram of water 1 degree Celsius, where it only takes 0.45 joules of energy to heat 1 gram of iron 1 degree Celsius. So that's almost a 10-fold difference. So specific heat values, really, I need you to know water, okay? Other ones I would give to you or you would have to calculate. I need you to know water. Water is key. We use a lot of experiments involving water and dissolving in aqueous solutions, so water is commonly used. So that's a value you should feel comfortable with. Fun fact, 4.18 joules is equal to a calorie. Okay, so those numbers are the same. Back to our example. Let's try one. If a 2.65 gram sample of water was heated from 25 degrees Celsius to 37 degrees Celsius, how much energy was used to heat the water? So our equation is Q is equal to MC delta T. It's asking about how much energy, so we're solving for Q. So Q is equal to M is the mass. We're told this is a 2.65 gram sample of water. C is the specific heat. Since we're talking about water, we're going to use our 4.18 joules per grams times degree Celsius value. And then remember, delta T stands for the change in temperature. So the water was heated from 25 to 37 degrees Celsius. So that means the temperature was raised from 25 to 37. So it changed by a value of 12. So that's going to be my value here, is 12 degrees Celsius. So then you would just go ahead and plug in and solve. So 2.65 times 4.18 times 12, 2 sig figs, I'm getting 130 joules. Okay, remember, because specific heat is joules per grams times degrees Celsius, the Q will come out in joules. All right. An extension question for you. If a 2.6 gram sample of iron was heated with the same amount of energy, would the temp change be more or less? So you heat iron with 130 joules of energy. Would the iron get hotter than the water or less hot than the water? Well, let's look at these values again here. So iron has a smaller specific heat. It takes less energy to heat it. So if you're heating them with the same amount of energy, the iron temperature difference would be more. The iron would get way hotter with 130 joules than the water would because it takes less energy to heat the iron. Here are a couple more examples that want you to use Q is equal to MC delta T in order to solve for various variables. I would encourage you to pause the video right now, give a couple of these a shot, and tune back in when you're ready. All right, here we go. There's a few things I want to highlight as you are going over your answers here. The first one being this. Notice how this was 32 kilojoules. Whenever we're using Q is equal to MC delta T, it's always in joules. So you need to make sure that's converted to joules first. This was asking for what was the final temp. Remember, when you're using Q is equal to MC delta T, you're solving for delta T, so you're solving for the change in temperature. So I solved for that change in temperature, so that's how much the temperature shifted. And so if it was initially at 20 and it shifted by 38, that's why my final answer is 58. You also could have solved for T final within the equation itself, and that would have worked too. That's just more complicated algebra, so I did it this way. So either way works. For the next one, the key here is making sure that you're picking the correct variables. So I told you that 4 grams of sodium hydroxide is dissolved in 150 mils of water. Well, notice it says the temperature of the water raises. So if what we're measuring is the change in temperature of water, we should be using the specific heat of water which means we should be using the mass of water. So basically the 4 grams of NaOH in this example is negligible. We don't need to know that. Basically what we're measuring right now is the energy of the water specifically. And so that's why I use the 150 mils. In the earlier example, I told you that the density of water is 1. What that means is a mil of water is a gram of water. That's something that could just kind of be in your head as well. So know that you can translate milliliters of water to grams because it's just a 1-to-1 conversion. Make sure you're being careful with sig figs. 11.0 should have 3 because you should be lining up to the 10th place, and that's why I wound up with 3 sig figs in my answer here. So these are just some common mistakes. So just something to make sure that you're looking out for as you're doing some more example problems. All right, so using that previous example, we are now going to determine the delta H of the reaction. So notice we've got delta H reaction here. That's just an overall term. So delta H of a reaction, it could be a chemical reaction. It could be kind of any change. So that's more of an overarching delta H value, or sorry, delta H subnote. So same values as before. So what we're going to do is we're going to figure out delta H. So a few things that we need to remind ourselves of, some questions we should be asking ourselves before we go ahead and answer this. What is the system and what is the surroundings? Okay, so 4 grams of sodium hydroxide is dissolved. Remember, one of those things that can kind of help you figure out the system is actually writing out the reaction that's taking place. So if I'm dissolving sodium hydroxide is ionic, so I would be taking sodium hydroxide solid. It would dissociate into its ions and look something like this, and it would be aqueous because it's dissolved. So my system must be the NaOH. So that's what's actually causing the energy shift. So that means that the surroundings is the water and everything else on top of it. So this will be key here coming up in just a sec. Is this reaction endo or exothermic? Well, let's look at the data here. It looks like the temperature of the water was raised. So the temperature of the water went up. Okay, so the temperature of the water went up. We just said that the water was the surroundings. So if the surroundings are getting hotter, if the temperature is going up, we're going from system to surroundings. So that means energy is leaving the system. So this is going to be an exothermic reaction. And as you may remember, that means delta H is going to be negative because energy was lost from the system. So again, are the surroundings gaining or losing heat? Gaining, kind of that same idea from above. How much energy is transferred? So we're actually going to steal our answer from the above example. So all of these values stayed the same. So we solved for Q. So Q is going to be 6.90 kilojoules. I'll take the kilojoules value rather than the joules value, because if you remember, all these values are always per mole. So how much energy is transferred? 6.90 kilojoules. That is the amount of energy that left the system and went into the surroundings. Because what we were actually measuring is Q of the water. Because we did the mass of water, we did the specific heat of water, and we did the change in temperature of the water. So we actually solved for the Q of the water. So this is how much energy got transferred to the water. Keep that in mind. Moving forward with this, remember the units for delta H are always kilojoules per mole. You can do joules per mole, honestly, it's fine. Kilojoules per mole is just way more common. So if the energy is equal to kilojoules per mole, basically we then need to divide this by the moles of the system. So let's remind ourselves, we said that the system was the sodium hydroxide because that's what was causing the temperature shift. So we had, whoa, what's that? What's happening? Stop. Okay. We had 4 grams of NaOH. Okay, let's get this to moles, because this is always this is always kilojoules per mole. Adding up NaO and H is going to give you 40.00 grams of NaOH per 1 mole. 4 divided by 40, I am typing this in my calculator because my brain's not working. Yeah, 0.1, that makes sense. 0.100 moles of NaOH. So remember, the amount of heat that was released was 6.90 kilojoules. That was released from the system. So if we want the kilojoules per mole of the system, I'm going to take my 6.90 kilojoules and I'm going to divide it by the 0.100 moles. So 6.9, I'm doing this in my calculator again, don't judge me, 69. So, keeping with my 3 sig figs, my final answer is going to be 69.0 kilojoules per mole. So remember, our initial question was we were determining delta H of the reaction. Okay, so we wanted to know what the delta H value of this was going to be. One of the earlier questions we asked ourselves was this reaction endo or exothermic? We went with exothermic because the water, which was the surroundings, got hotter. So when coming back to our initial value here, we need to once again ask ourselves, was this endo or exothermic? The answer was exothermic, so we also need to make sure that we're including our negative sign. So my delta H of reaction, how much the energy changed within the system, and remember the system was the sodium hydroxide, energy left the sodium hydroxide, that's why it's exothermic, that's why it's negative, that's why the water got hotter, that's why I'm including a negative in my final answer. So basically you're just doing that Q is equal to MC delta T equation, and then if you want to figure out the delta H and you want to get that initial, can you not? If you want to get kilojoules per mole, you just need to take your kilojoules value and then divide that by moles, and you just need to make sure that you're aware of what the system is. Let's do another example. So we've got 32.3 grams of that, and we are reacting it with 250 mils, a 250 ml solution of barium hydroxide. The temperature of the solution raises from 21.0 degrees Celsius to 34.6 degrees Celsius. So looking at our variables here, what is the system, what is the surroundings? So I've got 32.3 grams of this, and I'm reacting it with 250 ml solution of barium hydroxide. So my system in this case is going to be the HC6H7O6, and my surroundings is going to be the solution that I'm mixing it in. So one of the key words here is solution. So if this is a solution, it's dissolved in water, right? So that's something to be aware of. So something's in a solution, that means it's in something, it's in water, basically. Is this reaction endo or exothermic? Well, it looks like the temperature went up of the solution, so that means it's exothermic, heat is being released. That means the surroundings are gaining heat, and now we need to ask ourselves how much energy was transferred. So basically when it's asking for how much energy, it's asking for Q. So we'll go ahead and solve for that. So we've got Q is equal to MC delta T. So we're going to go with the 250 ml solution. Again, we're going to go with that, and then since it's a solution of water, you can just go to grams. Because I know the specific heat of water is 4.18 joules per grams times degrees Celsius. I don't know what the specific heat of this thing is, okay? If I did, it'd make things a lot easier, but since we do a lot of these reactions in water, and water is such a common specific heat, we generally calculate the Q of that. Delta T is going to be my change in temperature. So it went from 21 to 34.6. So I'm going to subtract 34.6 from 21, and I'm getting 13.6. All right, so I can go ahead and figure out Q from there. So 250 times 4.18 times the 13.6. This was 250 dot. So this technically had 3 sig figs along with everything else. So I'm going to go with 3 sig figs. 14,200 joules. All right. So if now I want to figure out the delta H of my reaction, remember that's kilojoules per mole. So now I've got the joules part. I could quick convert this to kilojoules if I wanted to and divide this by 1,000. And I would get 14.2 kilojoules, but I need to get the per mole part. And it's always going to be of the system. So our system, it looks like, was this 32.3 grams. So I'm going to take the 32.3 grams, put it over 1, convert grams to moles using good old stoichiometry. So I'm going to figure out the molar mass of this compound. So I've got 6 carbons, so that's 12.01 times 6. I've got a total of 8 oxygens, so 1.01 times 8. And then I've got a total of 6 oxygens, so 6 times 16. Sorry, I did that all a little fast. For a review of a basic concept. So that's 176.14 grams per 1 mole. 32.3 divided by this value to 3 sig figs, I'm getting 0.183 moles. Okay, I'm looking for delta H. I've got my kilojoules, I've got my moles. To get kilojoules per mole, just go ahead and divide them. So 14.2 kilojoules divided by 0.183 moles. 183. Yes, hello. You're cute. I'm getting 77.6 kilojoules per mole. And then the last thing you have to ask yourself is this value positive or negative? That communicates whether this was an endo or exothermic process. Was this heat leaving the system or was this heat entering the system? We said this was exothermic because the water temperature was raised, so the final answer for this will be negative 77.6. So that's just something to be really mindful of. Go ahead and try this example, pause the video, and check in when you're ready. I'm not done with the answer. I just wanted to let you know what my working conditions are right now. We must be held in this moment. All right, here we go. So you would solve for Q, again, making sure you're using the correct variables. You would be working with the solution, so you can use the 4.18 for your specific heat of water. You would convert the grams to moles, and then in order to get this final value, I took 9 divided by 0.453. So I did the kilojoules divided by moles to get that final value. I had the value be negative because the temperature increased, so the surroundings got hotter, so this was exothermic. The thermochemical equation, you were mixing 16.5 grams of hydrochloric acid with sodium hydroxide, so this was a double replacement flashback. So I did the hydrochloric acid with the sodium hydroxide, switch the cations, the metals around to get sodium chloride and water. You could have also written the water as HOH too. Since this was exothermic, I put the kilojoules as a product. You could also do the semicolon notation and still make sure that it is written as negative. And it's all good to go because this is kilojoules per mole, and I only had 1 mole of hydrochloric acid on either side, so I didn't have to change this value at all. So that is Q is equal to MC delta T and how we can use it to figure out the delta H of different reactions.